Hello and welcome to Project 152, your weekly exam prep. Now every week we cover some questions from past QCAA papers. If you stick with us until the end of the year, you'll have done every single question the QCAA has ever done. Now this is week 13 and we're running through the questions from last week. Link in the description to next week's questions. Let's get started. So we kick off with a partial fractions question and it says, if you want to integrate this, it can be determined with these partial fractions. And so the question is, what is the value of A? Interesting question because you've got to understand that it's not just a normal procedural turn this into a partial fraction. Instead, you need to understand that because this is equivalent to this, if you just do this sum here, you'll figure out what A is. So let's do that sum. So here it is, and it's like an algebraic fraction style question that I would do with a year 10 student from here. So how do we do it? Well, when we want to add two fractions together, we need to make the denominators the same. And the way to make denominators the same is just, the easiest way is just to multiply them by each other. So this is going to be 1 plus x times 1 minus x on this side here. And here, we need to do the same top and bottom. So it's going to be negative 1 times what I just multiplied it by, 1 minus x. All right, and then we're adding 2, and we're going to multiply that fraction, top and bottom, by this denominator, 1 plus x. Now the reason we do that is because now we get 1 minus x times 1 plus x, and you can see that these denominators are the same now. So that means that we can add them together with the same denominator. Now when we expand this, we're going to get 1 squared, which is 1, x, negative x, so they cancel each other out, and we end up with a negative x squared. Not surprisingly, because you can see here a 1 minus x squared. Okay, and then we're just expanding all these brackets and grouping them. So negative 1 times 1 is negative 1, negative 1 times negative x is positive x, plus 2 times 1, which is 2, plus 2 times x, which is 2x. All right, finishing this off, we have x and 2x, which is 3x. Not surprising, because we have a 3x up here. And then it says minus, and then minus 1 plus 2. Okay, minus 1 plus 2, that's positive 1, right? Okay, that's interesting. 1 minus x squared. All right, and you have to be very, very careful with how you answer this question. It's asking what the value of A is, and we can see here that 3x minus A is equal to 3x plus 1. The 3x's cancel each other out, and we get negative A equals 1, which means that A is equal to negative 1. A lot of people think the answer is positive 1 because you're looking at a positive 1 here, but because of the way the question is formulated, you've got to be very careful. My answer is negative 1. All right, celebrate, keep going. So a very interesting question here and one that a lot of people have trouble with. So what's going on? We've got a system of 3 equations of planes, and you can see 2 of them are parallel. And so it's the parallel bit that's kind of the important part of this question. All right, let's take a look. We have 2 equations. Let's just write them down. So the question, first of all, is, are these 2 ones the parallel ones? Or is one of these like this one and the other one the straight up and down one? Okay, so a key idea here is that 2 planes, here's a plane, here's another plane. 2 planes will be parallel if their normals are in the same direction, right? And so their normal might be this, but their normal might also be this. Their normal might be expressed as this. A big long one or a big short one, when it comes to these normals, it doesn't matter as long as they're in the same direction. Okay, so what are the normals of these 2? Well, it's easy to find the normal of any equation of a plane. You just look at these coefficients. So an equation of a vector that is normal to this plane would be, and let's just write it here, 1, 1, negative 1. 1, 1, negative 1. Okay, what about this one? This is 1, negative 1, negative 1. 1, negative 1, negative 1. Okay, now, these are not parallel to each other. How do I know that they're not parallel to each other? Because there is nothing that I could multiply one of them by to make it equal to this one. All right, let me just write that in like mathematical notation. So I've called this normal 1 and I've called this normal 2. And what I'm saying is that normal 1 does not equal normal 2 multiplied by any k value. There is no k value that I can multiply one of these normals by to make it equal, all right? Then it's never going to happen. But that means that one of these must fulfill that criteria. One of these must have a normal that is parallel to either this or parallel to this. So let's see if we can, well, actually, let's just write down all the normals for all of these. All right, what a wonderful question. So I've written down my 4 normals, all from here, right? So I look at here, 2, negative 2, negative 2. That's this one here. And the next one is like 2, 2, negative 2. That's that one there. I'm just looking at the coefficients and writing down normals. Okay, now look at this one, look at this one, right? 1, 1, negative 1, and this one says 1, negative 1, negative 1. What I notice when I look at this one and compare it to this one, right, is that if I just multiply this by 0.5, I'm going to end up here. So these normals are parallel, and that's what I said we needed. We needed 2 normals that were parallel. So that's probably our answer, but it isn't, and I'm going to explain why. All right, what about this one? 2, 2, negative 1, 2, 2, negative 2. Well, this fulfills that criteria as well. Uh-oh. All right, let's keep going. 2, negative 2, 2. All right, that's got a negative in the middle, right, and 2 positives. There is nothing that I could multiply this by to get to either one of these, because they don't follow that pattern. And what about this one? 2, 2, negative 2. Well, that looks identical to this one. So that one works as well. Oh man, okay. So that's not great because I've used one idea and I've got 3 potential answers. So what's the other trick we need to pull? Well, the trick is that one of these planes, or maybe 2 of these planes, aren't just parallel to each other. They're sitting on top of each other. They're equal to each other, right? So let's look at A, because A is a potential candidate. 2, negative 2, negative 2, 1. And then look at our original ones. 1, negative 1, negative 1, 0.5. If I take this and just multiply everything by 2, 2x minus 2y minus 2z equals 1, I haven't changed the equation. It's exactly the same equation. And it's also this equation. So these are not 2 parallel planes. Well, technically they are 2 parallel planes. They're actually 2 identical planes. They're sitting on top of each other. So they don't fit this. So that one's not going to work. That one's not going to work. All right, what about this one here? 2, 2, negative 2. Okay, now the 2, 2, negative 2 comes from equation 1 here. It has the same problem. If I multiply this equation by 2 across here, 2, 2, 2, 2, I haven't changed it. It's the same equation. It's just that now it looks identical to that, and so those planes are sitting on top of, they are the same plane. This does not suffer from that problem, right? If we look at our last one, 2, 2, negative 2, 3, there is no value that I could multiply my entire equation by to make it look like this. These are different planes, but they are parallel to each other because they have the same normals. Big question, big question. Let's tick it. Do I think that maybe this is the question that students got like the most wrong last year? Let's check. All right, so this was question 9 last year, and if we look at our solution here somewhere, there it is. Only 28% of students got it right. It's almost like a pure guess. Now, it's not the question that students got the most wrong. That was question 7 last year, where only 15% of students got it right. I just checked that out. We didn't have the knowledge to do that question yet, but looking forward to it in a few weeks. All right, that was our equations of planes. I'm going to celebrate that one, and let's move on to our short responses. All right, so we've got some sort of inverse tan function. Now, a lot of us might not be comfortable with what that looks like, but there is some interesting clues as to what it looks like. It says, for suitable values of x where f of x is in the set of negative pi on 2 to pi on 2. So that tells us that it looks something, well, actually it doesn't really tell us what it looks like, but it does tell us that f of x, the range of f of x, is between negative pi on 2 and pi on 2. So that means that our function exists between pi on 2 and negative pi on 2. Okay, and if you do have some experience with arctan and you can remember sketching it, then it looks a little bit like that. That's what arctan looks like. Now you can do all of this without knowing the general shape of arctan, but that's what we're dealing with. All right, it says determine f of 2, and you can see it's a 1 marker, so you just need to find the answer. I'm just going to put it like here somewhere. I don't actually know where it is, but I'm just going to put it there, and then let's find that value. Straightforward, we're subbing it into our equation. All right, so I've drawn it here. F of 2, inverse tan, 2 on 2. So I've just subbed 2 into here. Now, obviously, that's equal to the inverse of 1. Now, a lot of students have trouble with this, but really you're just solving a trig equation, right? Like, imagine, it doesn't, but imagine it was like theta equals inverse tan 1. We could rewrite that as tan theta equals 1. And you've all had experience solving that. When you solve that, you find the inverse of it, and you should know that if tan theta equals 1, then theta equals pi on 4. So our value here is pi on 4. Now, we really don't need all of this. You should be able to do all of that in your head. Well, probably don't need that and don't need that. That's better. So inverse tan 2 on 2, it's the same as inverse tan 1, and you should know that inverse tan 1 equals pi on 4. So what does that mean for my little picture here that I've drawn? That there is a coordinate of 2 pi on 4 sitting right there. That's going to be important because I'm sort of looking into the future. I can see what's coming up next. Before I move on, it's probably worth mentioning that there's kind of could potentially be other values. Remember that this is just like a tan function that's been inversed, so 45-degree angle and rotated this way. You've actually got a bunch of these that would be all stacked up on top of each other if it was just a relation, but it's a function. So you've only got one answer, pi on 4. We don't have multiple rotations around the circle. All right, part B, f dash of 2. So we're going to have to find the derivative of this. So if f of x equals inverse tan x on 2, finding the derivative of that should spark you to look at your formula sheet. There we go. So f dash of x is going to be equal to, and then we just do what it says here. So it says x on a, which is what we've got here. We've got an x on an a. That's going to be equal to a over a squared, so 4 plus x squared. Fantastic. Now, they're not asking us to find the derivative. They're asking us to find the value of the derivative when x equals 2. So we need to sub 2 into that value there. So 2 over 4 plus 2 squared. So that's 2 over 8, which is 1/4. All right, that's important. Now, I think this is important information. I think this is important information because I've looked into the future. I can see what they want me to do next. Now, they want me to find the equation of the tangent to the graph at this point here. And so what do I have? I have a point, 2 pi on 4, and I also have the gradient at that point, m equals 1/4. Okay, I've got all of this information summarized now on my picture. So I'm going to get rid of this so I can work out my final equation of the tangent. So it's an equation of a straight line, so it's y equals mx plus c. And I know a point on the line is 2 pi on 4. So y is equal to pi on 4, and x is equal to 2. And I know that m, the gradient, is 1/4. And then we have this plus c on the end. All right, now I can solve for c. I know that c is equal to pi on 4 minus 1/4 of 2, which is half. Pi on 4 minus 1/2. I guess that's pretty good. I've got a c value now, pi on 4 minus 1/2. So I can finish this off by saying, therefore, y equals m 1/4 x plus my c value, plus pi on 4 minus 1/2. Just make sure you're comfortable with this. This happens a lot in external exams. When you find the equation of a tangent, it's not as straightforward as just number. Sometimes you end up with these weird things with a pi on 4 and a constant. Sometimes you end up with like e in there or ln in there. So just keep in mind, they're not always going to be nice and neat, as tends to happen in like textbook questions and things like that. All right, one last question in today's set. Very important to celebrate though. Last question. Last question here, and we've got position vectors, and we're talking about velocity vectors, and then we're talking about collisions and things like that. All right, so we've got a position vector given here, and we're told to determine the velocity vector. So, position vector, velocity vector. We've got the position vector. We need to derive that to find the velocity vector. So we should be able to do this in a single shot. The velocity vector for particle 1 is equal to the derivative of this. So the derivative of 2t plus 1 is just 2, and that's our I component. And the derivative of t plus 3 is just 1j, so plus j. And there's this one here you've got to be a little bit careful with. So the derivative of negative 2t plus 3k, right? So I've just sort of expanded that bracket. So the derivative of negative 2t is negative 2, so we've got negative 2k. All right, there is our velocity vector. That gives us a single mark. Now this next question is a bit of a classic. It says, determine the time when the position vector, there's the position vector, is perpendicular to its velocity vector. All right, so two vectors that are perpendicular to each other. The minute you hear about two vectors being perpendicular to each other, you should be thinking about the dot product. Because the dot product, when two vectors are perpendicular to each other, is equal to 0. All right, so let's figure out a way to sort of show that. So 0 is going to be equal to the dot product of, and I'm going to write these vector equations in column form because I find that easier to do the dot product. All right, so we've got a 2t plus 1. We've got a t plus 3. And then be careful here, we've got a negative 2t minus 3. All right, and then here, this is where I'm going to do my velocity vector, and that's the one I just found. Much easier. 2, 1, negative 2. Okay, after that, I'm just doing the dot product, which means I'm doing this times this, this times this, and this times this. Okay, so writing this out, we've got 2 times 2t plus 1, so that's 4t plus 2. And then we have 1 times t plus 3, so that's just t plus 3. And then this last bit just is super messy, so you just got to be careful. It's negative 2 times negative 2t, so that's positive 4t. And then it's negative 2 times negative 3, so it's negative 2 times positive 3, which is negative 6. And all of that's going to be equal to 0. All right, we can group all of our t's. 4t plus 4t is 9t. And we've got our 0 there. And we've got a 2, a 3, and a negative 6. So negative 6 plus 5, I think that's negative 1. Okay, so 1 is equal to 9t, and t is equal to 1/9. Okay, so at time 1 over 9, that's when our position vector and our velocity vector are at right angles, are perpendicular. It's good practice to look for your units. It's in seconds. So after 1 over 9 seconds, that's when those two vectors are going to be perpendicular. Okay, finally, we need to determine whether the two particles collide. So we've got this particle here, we've got that particle there, and we need to figure out when they collide. Interesting part C here, because part C really doesn't have anything to do with part A or part B. Part A is all about finding that velocity vector. Part B is about finding something else to do with the velocity vector. But if you want to know where two particles collide, you don't care about the velocities at all. You just want to know when their positions are the same. All right, so I'm going to get rid of that, and we're going to solve part C. Now, their positions are the same when their I coordinates match, when their Y coordinates match, and when their J coordinates match, and when their K coordinates match. So let's make the I coordinates match first of all. All right, so let's look at our I coordinates first. 2t plus 1 equals 16 minus 4t. Grouping these together, we get 6t equals 15. So t equals 15 over 6. Simplifying that, dividing top and bottom by 3, we'll get 5 over 2. Okay, so these two particles x coordinates match, or I coordinates match, at time 5 over 2 seconds. What about its j components? When do they match? All right, we have t plus 3 equals negative 3t plus 13. I've just expanded these brackets, negative 3t, positive 13. When we group that, we'll get 4t equals 13 minus 3, which is 10. T equals 10 over 4. And simplifying that, we get 5 over 2. Okay, great. There is a time, and that time is 5 over 2, 2.5 seconds, when this particle's I and J coordinates match. All right, now, if their K coordinates match at the same time, then we're in business. So let's do exactly the same thing for K. All right, so I've got negative 2t plus 3, I've just expanded the brackets, is equal to 2. All right, so what have I got there? I'll write it as 2t equals 3 minus 2, which is 1t equals 1/2. So that's a big problem, right? Because yes, they have this, it has the same I coordinate and the same J coordinate at time 5 over 2, but its K coordinate is the same, not at 5 over 2. It's the same at 1/2. So what does that mean for us? Well, if you imagine one of the objects is like traveling along like this, right? And one of the other objects is traveling along, say, like this, right? But one is higher than the other. You can imagine like two flying cars, where one flying car drives along like this and the other flying car drives along above it, right? There is a moment when its I and J coordinates are the same, but they don't crash, because the time when their heights are the same is at a different time. Their heights were the same over here somewhere, right? Their heights are different here, so they're not going to crash. Okay, so what was the question? Determine whether the two particles collide. No, they do not collide, because there is no time when their I, J, and K components are all equal at the same time. So, no. So I've stolen the QCAA's wording here. The particles do not collide as the solutions are not consistent. The solutions are not consistent. All right, let's celebrate. All right, that's it. That is week 13. Link in the description to next week's questions. It's tech active again. Hopefully you're getting good with your calculator, but you do want to make sure you've got it with you and you're working out all of those little things. And I will catch you next week.